Okay, now let's look at Faraday's law. So we looked at induced current and induced EMF. Let's try to calculate the magnitude using Faraday's law. Okay, and this is Faraday's law in short, that the magnitude of the induced EMF is this, delta phi divided by delta t. So E is the induced EMF, that's like the voltage you induce in the moving conductor or in any conductor. And delta phi is the change in magnetic flux, and delta t is time taken. So this law says the faster the magnetic flux changes, the bigger the induced EMF. Okay, or well, let's go to the magnet example again. So we had a magnet falling through a loop. Yeah, so if the magnet is falling faster, if it's traveling faster, you will have a bigger current induced in the loop. So you will have a bigger EMF induced in the loop that will produce a bigger current. So that's what Faraday's law says, that the induced voltage, the induced EMF depends on how quickly the magnetic flux is changing. Okay, so altogether this ratio, delta phi over delta t, is known as rate of change of flux. So induced EMF is the same as rate of change of flux. And once we have the EMF, we can use Ohm's law to find the current, and we then have to factor in the resistance as well, because the EMF is like a voltage, and Ohm's law says to find the current, you need to factor in the voltage and the resistance. Okay, so Ohm's law and Faraday's law will give us the magnitude of the current, and to find the direction, we use Lenz's law. Okay, so about the flux increasing or decreasing, that will give us the direction of the dipole moment, that will give us the direction of the current, like we have done in the previous slides. Alright, so this equation applies to a single loop. Okay, and if you have multiple loops, then you just have to multiply this quantity by the number of loops here. Okay, so if you have like 10 loops, you'd multiply this ratio, the rate of change of flux, by 10. Okay, so let's look at rate of change of flux, the delta phi over delta t. Okay, so this is what delta phi is, the first line in the box. Delta phi equals phi final minus phi initial. So we have a system, we have a loop where the flux is changing. So the flux starts from some initial value, ends up at final value. If you subtract the final and the initial, you get the delta phi. Okay, and then we have our equation in the next line, delta phi equals A times B, area times field times cosine theta. Okay, let's underline this. Now, let's say your flux is changing, and your flux is changing because just one of area or field is changing. Okay, not both, just one of them is changing. Okay, so let's say your area is getting bigger or smaller, or your field is getting stronger or weaker, and you're trying to find how much the flux changes. So this is what you can do here. You can just change the above formula, put a delta phi on the left side, and then put a delta for the quantity that's changing. If the area is changing, you put a delta A. If the field is changing, you put a delta B, and everything else remains the same. Alright, so this applies once again when only one of area or field is changing, not both. And then the next point here, if you know the rate of change of area or field, delta A or delta B, so if you know how much time it takes, we can just introduce a time on both sides. So on the left side, we can make it delta phi over delta t. On the right side, make it delta A over delta t or delta B over delta t. Okay. All right. So once again, if only one of area or field is changing, you can do this. You can treat the area or the field as a changing quantity. Everything else is constant. And now we can look at the last the note at the bottom. If theta is changing, you can't do what you did above. You have to do the full form. You have to find the final flux, you have to find the initial flux and subtract them. Okay, so you can't just use the shortcut that we have talked about, area or field. And the reason is that the theta comes with a cosine function in it. So the calculation for it is more involved. You have to use the full form of the. Let's look at an example. We are trying to find the induced current in this system. We have a circular copper loop and with a small resistance, 5 milliohms, and we have its radius and area. So its area is 0.0707 meters square. So the area is already given. We don't even need the radius. and here the magnetic field is decreasing. Okay, so we have magnetic field pointing into the page. Right, and it's decreasing, and it's decreasing at a rate of 0.5 millitesla per second. So what does that tell us? That tells us when we do delta B over delta time, it's equal to negative 0.5 millitesla per second. All right, and negative sign means that is decreasing. Yeah. And we are looking for the induced current. We are looking for I. Okay, so let's write down our information here. We have the area, the resistance, and we have theta of 0 degree. How do we know theta is 0 degree? Because the loop is flat. All right, so the loop is parallel. The field is parallel to the loop's axis. So here the loop is flat. The axis of the loop is pointing up, straight up or straight down. And the external field is also pointing into the page or out of the page. So they're pointing in the same direction. We have an angle of 0 degrees. And delta B over delta T is negative 0.5 millitesla per second, as we says. Okay. So as the field is changing, the flux is changing, and because the flux is changing, we should have an induced EMF in the loop, an induced voltage in the loop. Okay, let's continue. So this is what we do. We use Faraday's law. EMF equals delta phi over delta T. All right, and how do we find delta phi? So here only one quantity is changing, only the magnetic field is decreasing. So we can write delta phi as this, delta B over delta B times area times cosine of 0. Well, let's put cosine of theta. Okay. All right, so remember that if only one of area or field is changing, you can just put a delta for the quantity that's changing, and everything else remains the same. All right, so that's what we have here. In the next line, we have delta B divided by delta T, okay, multiplied by area times cosine theta. And now let's plug in our numbers. So we already know what delta B over T is. We know what the area is. We know what the angle is. Okay, and you plug in these numbers, you get an EMF of 0.034 millivolts. All right, so we get the EMF here, and you plug it into Ohm's law. I equals EMF over R. So you divide millivolts by milliampere. Here, let's put the units. So you divide millivolts by milliohms, and you get 7.1 milliamperes, right? Let's make this a volt. All right, so this gives us the current in the loop. We used Faraday's law to find the EMF, and we used Ohm's law to find the current. And to find the direction, we can use the same strategy that we have used for the earlier examples. We know that the external field is pointing into the page and the flux is decreasing. So the induced EMF must be in the same direction as the external field, and it must be pointing into the page. And if induced EMF is into the page, you can use the right-hand loop rule and get clockwise current. So the current is clockwise of 7.1 milliamps. Okay. Now let's look at how to find the induced EMF when a loop is entering or exiting a box, a region here. Okay, so we have a square loop of sides 1.5 meters, and it's moving at a constant speed of 2 meters per second. So that's the velocity, and it's moving from a region that has a magnetic field of 3 millitesla. Okay, so it's inside the box the field is 3 millitesla, outside the box is 0. And it's the loop is flat, so that the axis of the loop is parallel to the direction of the field. Okay, and we are trying to find the EMF as it leaves the field, so as the loop exits the box. Okay, Alright, so let's set up our argument here. So we know that EMF is only induced when the loop is entering or exiting the region, not when it's in between, not when it's completely inside. And the induced EMF depends on the velocity, because depending on the velocity, the area changes fast or slow. Okay, so we are looking at change in area, delta A over delta T. And this delta A over delta T depends on the velocity. So the faster it moves, the faster the area changes. We have to calculate exactly how. Okay, so let's try to figure out how the area is changing. So let's say at time of t initial, okay, so we're looking at time in initial, we have the loop somewhere over here. Okay, so at some location x initial. All right, fine. And then at a different time of t final, the left edge is a different location, x final. Okay, so let's mark x initial and final here. So suppose here this is x initial on the left. Okay, so this point is x initial and this point is x final. Alright, so our loop moves from x initial to final. It moves a distance of delta x. Circle it. So delta x equals x final minus initial. So we don't know what x final is, we don't know what x initial is, but we know there are two different locations. And then if we multiply the delta x by the 1.5 meter, the side of the square, we get this blue area. Okay, so this blue area is our delta A. Alright, so this blue area is a delta A. It depends on delta x, how much the loop travels in this time, and also on the side of the square, the 1.5 meters. Okay, so now let's look at the box here. We are trying to find delta A over delta T, and delta A, like I said, is the shaded region in blue. So our edge of the square travels from x initial to x final, travels the distance of delta x, and we are looking for the area of the blue triangle. That's our delta A. Okay, so this is what we do. So delta A equals L times delta x. So if you we can see that in the picture. Delta A is the blue rectangle. The shaded region is multiplied by delta x by L, the two sides of the rectangle. And then you divide by delta t. Okay, so if you divide by delta t, you do it on both sides. You have delta A over delta t on the left side. You have L delta x divided by delta t on the right side. Now let's look at delta x over delta t. That is the definition of velocity. Okay, so we know velocity is distance over time, so that's the delta x over delta t. Right, so this gives us our final equation here. Delta A over delta t equals velocity multiplied by length. Alright, so here our loop is moving at some velocity, and if you multiply this velocity with the side of the loop that's exiting, we get the delta A. Well, delta A over delta t really. So this we can use. Okay, continuing. So we use Faraday's law. Faraday's law equals delta phi over delta t, and here like before, for delta phi we have only the area changing, so we'll replace the delta phi by delta A over delta t times b times cosine of 0 degrees, cosine of theta. Alright, so delta phi equals delta A over delta t times b cosine theta. So we plug all this in here and then plug in our numbers. For delta A over t, we replace it with L times v, so like in the previous slide. And angle theta is going to be 0 degrees because the loop is flat on the ground and the field is pointing straight up or down. And we get this equation here. Okay, EMF equals B times V times L. And incidentally, that's the same as what we derived in an earlier slide using the right-hand cross product rule. So this proves that whether you use the right-hand cross product rule or whether you use this method, you end up with the same equation, equation for the induced EMF. All right, and we can also plug in our numbers, plug in the magnetic field, the L, the velocity, and we get 9 millivolts. Okay, and the current direction is going to be counterclockwise, something that we have solved earlier when we analyzed loop.
going to figure.